Alright, gang. So we're gonna start by doing another Gaussian elimination problem by hand. Remember we did a couple of these the other day? And then we'll flip over and we'll do a couple more on our calculators. And then hopefully we'll get to some other stuff today because I don't want to get too bogged down in this. But here we go. So I am on problem number 4 in 7.3. Everybody's paying attention, right? All right, so I'm going to write down my augmented matrix. So whether I am doing Gaussian elimination, which is what I'm doing.
I think we already did this one.
Oh, we already did that one? All right, good. Let's not do that one again. We're on number 4, right? And I wrote down number 3. Okay. So whether we are doing, thank you for stopping me by there, Gaussian elimination or Gauss-Jordan reduction, we need an augmented matrix. So we're writing down our matrix with our x's, y's, z's, and equals numbers all in a nice little columns there. And making sure I haven't copied anything wrong. Okay, keep an eye on it. Now, what's our objective? We're doing this by hand without a calculator. Liam, were you putting your hand up?
No.
You know what our objective is?
They get zeros and ones.
Exactly. So I want to get zeros here first, right? That's where I want zeros. So I'm going to go ahead and recopy my top row. I don't need any zeros in that row if I am doing Gaussian elimination, which I am. Now, my job is to somehow add these together and make that go away. Well, that's easy, right? It's set up for that. So when I add these together, I'm adding the equations. I'm adding the rows together. I'm doing regular elimination. So that's 0, -1, -4, and 7. Everybody with me? Now the next one's gonna be a little harder. I'm gonna do the same thing. But these aren't set up to eliminate. So I'm going to have to do what? Multiply the top row by -5. So I'm going to do that. Some people can do it in their head. I have to write it down. So I'm going to write it right down here. That new row, I'm going to times it by -5. It's going to be -5, 15, -5, -20. Now I'm going to add them together. So then I get my 0, 2, 8, and -12. Does that look all right? Don't let me make a mistake. Okay. Now, if I'm doing Gaussian elimination, there's only one more 0 I need. And where is it? 3, 2. This guy right here. The 3. Somebody said the 3, 2 spot. 3rd row, 2nd column. That's exactly where I need it. Lucy?
Can that 1 be a negative?
It's going to be a positive in a minute, but I'm going to leave it a negative for now. You can change it at any time. So at any point you can change it. Ultimately it cannot, Lucy, but in the process it can be whatever, okay? Now I kind of like having it be a negative because it doesn't really matter. I need these two to cancel now, right? So I'm going to multiply that row right there, that 2nd row, by 2. If you make that a positive, Lucy, you're going to be multiplying by -2. So I'm going to times by 2 here, so I keep my 0, which is so important, and then -2, -8, and 14. All right, let's add. What happens? I get 0, 0, oh Lord, and then 2. Now, to Lucy's point, if the directions said Gaussian elimination, which they do, then the first non-zero number in every row has to be a 1. Now, I didn't just randomly change the sign. I divided this row by -1, perfectly legit. I divided this row by 2, perfectly legitimate, to divide both sides of an equation. However, something happened here that makes me a little bit uncomfortable. Exactly. The bottom row says exactly what Chris said. The bottom row says 0x, 0y, 0z equals 1. That's what that row says. Would everybody agree? And what does that mean? There's no solution. There's no solution. Now, to give you some sense of geometrically what's happening here, back in the beginning of the chapter, when we were doing regular substitution elimination, we were looking for where two lines cross each other, right? And usually they do cross unless they have to be parallel, all right? What we have in this case, these equations that are x's, y's, and z's are planes, like this. That's x plus y plus z equals something, okay? So what we've got here is 3 planes. Now, can 3 planes intersect in a single point? Heck yeah, right up there in the corner, aren't there 3 planes coming together? And that's what has happened to us before when we have come up with something like this, and we said, okay, z is 1, and then we figured out y, and we figured out x. We got a nice little answer like this. Well, this, they're not all intersecting. So you have something, think about a tent. Think about the 2 sides of the tent and the floor of the tent. Do all 3 of those intersect each other, all 3 at the same time? No, 2 of them intersect and 2 of them intersect, but they don't all 3 intersect, and that's what's happening here. These 3 planes have no points in common for all of them. Okay, easy enough. All right, girls, go ahead.
So I'm
Hey, get your calculator out.
still in like the very beginning when you were multiplying the second row
I didn't multiply the second row by numbers.
to cancel it out with
I multiplied the top row, and I added it. I didn't even multiply here.
no, to get rid of the like to make it so that the second and third row can cancel out, like the 0, 2, 8, negative.
I multiplied the second row by 2 and added. The second row is an equation. I multiplied it by 2. So then you use numbers. And I added those to the bottom.
It was the birthday.
And that's it. Sydney?
Sorry, I'm just a little behind still, so, the box furthest to our right, your left, why did you multiply it by -1 to get to?
Okay, you need to go back and watch the video and get the definitions.
Okay.
When we do Gaussian elimination, our matrix has to be in row echelon form. Row echelon form means the first non-zero entry in every row is a 1. That's the definition.
Okay, and it was -1 at first?
Yes.
Okay,
I mean, it came out to be -1 here when I did this addition.
no, okay,
So that -1 is that -1, and then I divided the row by -1 so it's positive.
oh, the second row, okay, thank you.
All right, calculators, now we're gonna do Gauss-Jordan reduction. So let's go back through this now. What's the difference when it says Gauss-Jordan reduction? Now, we're doing this on the calculator, but what's the difference? The end result matrix, or last matrix, will be in reduced row echelon form, which means that not only will these numbers be zeros, but so will these, right? That's the goal. All right, so here we go. You're gonna put this matrix in, and on these problems that are done on the calculator, I wanna see the matrix that goes in, and I wanna see the matrix that comes out. And I want you to tell me what button you press, which is going to be RREF, when the directions are Gauss-Jordan reduction. All right, do we need to, review how to put it in the calculator? We go to second matrix, edit. What are the dimensions of this guy? 3 by 4. If there's already stuff in there, don't worry about it, just type on top of it. Once you get that last entry in, second quit, back into second matrix, over to math, down to RRVF. Oh man, we got all kinds of weirdness happening today. Anybody notice anything about that matrix? Okay, now let's talk about this, guys. Let's talk about this. First of all, you need to understand there is like a huge difference between that equation right here and this equation. That one is not true, cannot be true, right? Which means no points are going to satisfy that. What does this bottom row literally say? No x's plus no y's plus no z's equals 0? Uh-oh, what about that? There are lots of numbers that could satisfy that, right? So how we depict that is we simply say z is something. Remember, the bottom row typically gives us z, or whatever your last variable is. So we're gonna say, okay, z is something. Z is something. Now, let's back up a row. What does this row say? Y minus 2z equals -2. If I knew what if I knew what z was, could I find y? Yep, but as it is, all I can say is -2 plus 2z. That's why I can't do any better than that, because I don't know what z is. Z could be anything. If you let z be 5, you would get a y value, but if you let z be 4, you would get a different y value, right? Back up one more. That says x plus 3z equals 5, which means x equals 5 minus 3z. That's the best you can do. Would everyone agree with me? It's the best I can do. Now, I want you to look at this for a second, and I want you to tell me if you can remember ever seeing x's and y's defined like this before. So x equals something plus something. Remember?
Oh, that can be a T.
Yeah, what if that's a t? Haven't you seen that before? And what did we call that? What was that when we had equations like that? What did we call them? Parametric equations. So we're gonna write our answer parametrically. Just like back then, guys, x and y back then were defined in terms of t. Now x and y are defined in terms of z. Okay? So how do we write that answer? Well, there are a couple different ways, but probably the most efficient way of writing it is to say, all right, x, y, z equals. Now, each variable consists of two parts, a number and what was a t part before, and now it's a z part. So I'm going to have a column for my numbers and a column for my parameter part. So x will be 5 minus 3z. Y is negative 2 plus 2z. Now, what about z? How am I gonna make z fit in that setup?
0 plus 1.
0 plus 1. Yep, you are exactly right. Okay, this is a point, and this is a vector. Believe it or not, you guys, this is a line. This is the equation of a line. This is a point on the line, and this is how the line moves. So this would be the equivalent of the slope, but I'm in 3 dimensions. So it says you're going negative, so start at this given point right here. You're going negative 3 in the x direction, 2 in the y direction, 1 in the z direction. And that's describing how the line is moving in space. So geometrically, we started with 3 planes, x, y, z, that's a plane. All right, x, y, z, that is a plane. We started with 3 of them. They all intersect, not in a point, but in a line. Can you envision that? It's like the pages of a book. Don't the pages of a book all intersect on the, what do you call that, binding or whatever that, you know what I'm talking about? Like right here. See, these are planes, and they're intersecting in that crease right there in the book. That's exactly what's happening here. So our first example, we had 3 planes that didn't intersect at all. In this one, we have 3 planes that intersect in a line. And the other day, we had 3 planes that intersected in a point. Exciting. All right, one more. I need you to do number 6. Now, do notice that number 6 is a little bit different because, well, tell me, what do you notice about number 6? We still have 3 equations, but now we have 4 variables. So when you set up your matrix, guys, be very organized about it. So I have my x's, my y's, my z's, my w's, and my equals. Does that make sense to everybody? So 1, 2, negative 3, 0. Now, Gauss-Jordan reduction means you're gonna RREF. What are the dimensions of this thing? Second matrix edit. 3 by 5. Anybody's matrix look like that?
Yes. The sheet.
All right, what do you think? Let's get creative. Let's think a little bit about this. What do you think?
W equals W.
So I have no idea what W is. So I'm gonna start out with W equals W. I think that's a great plan.
Did you?
I also don't know what Z is. I have no idea what Z is. It's not written here, guys, but I really need another row on this matrix because I need a row for every variable to make things come out nicely. and it's not there, so I didn't write it down, but look at this equation. What does that equation say? Y minus 2z minus w equals -1. You see what I mean? I don't know what z or w are. Y is -1 plus 2z plus w. And then the top equation says x is 1 minus z minus 2w. How does that look to everybody? Are you still with me? So now, my x and y are defined in terms of two variables, two parameters. So, x, y, z, w. I'm gonna have a number, I'm gonna have a z, and I'm gonna have a w. Does this make sense to everyone, that in order to kind of organize everything, I'm gonna need 3 columns this time? So 1 minus 1 minus 2 -1 plus 2 plus 1. Okay, now help me out. What do I do with z? It says z is z. So
0
plus 0.
0, 1, 0. There's no w's in z. And then what about the bottom?
0, 0, 1.
0, 0, 1. Perfect. Perfect. Now, I can't even, I don't even know what this is geometrically because it's 4 dimensions. So I'll let you really smart people figure all that out. But the structure of the solution is right there. This is called the general solution because this describes infinitely many solutions. And if you wanted a specific solution, what would you have to do? If you said, I want a specific solution, I want an X, Y, Z, and W, what would you have to do to get that? Pick a W and a Z. Because if you said, I'm gonna let Z be 1 and W be 2, could you figure out X and Y? Absolutely. But somebody else would pick different numbers and they would get a different. This is called specific solution. There's infinitely many of those. This is the general solution. Perfect, you guys are brilliant. Okay, solve on calculator using inverse matrix. I think we talked about this the other day, but I can't remember, so let's do it again just in case. Now, we're using our calculator, but we're doing it a different way. We're doing inverses. So the idea of inverses is that your answer, your X, Y, and Z answer, is going to be the product of your coefficient matrix, the inverse of that, times your variables. Okay, so these are your answers here. All right? Don't let that confuse you. To do an inverse, to solve with inverses, you simply multiply your coefficients times your variables, your original equals things. That's what I should have written. Okay? So we're going to put in our coefficients. 3, -3, 6, 1, -3, 10, -1, 3, and -5. Make sure I didn't make any mistakes there. And we're going to multiply the inverse of that matrix, which we can do on our calculator real easy, times this one. See, that's how we're going to find the inverse, or solve using the inverse. We did these by hand with 2x2s. We're doing this totally on the calculator. this time we have to put in two matrices. We have to put in this one, which is a 3 by 3, and we have to put in this one, which is a 3 by 1, so that we can multiply them together. So second matrix, edit, 3 by 3. And then quit out of that, and then back in, second matrix, edit, down to B, which is a 3 by 1. So I called this one A and this one B on my calculator. Now I'm literally going to multiply. I want to see this on my screen. This is what I want to see. So I'm going to second matrix, enter. There's A. And then I'm going to put my little inverse right here where this finger right here is pointing. There you have a button that says X
No
to the
ref?
negative first. No. Just second matrix. That puts A on the screen. And then put the inverse on. Times. And then second matrix down to B. Now I need B. And press enter. I got a decimal, I don't like it, so I'm gonna go ahead and press math, frac. And I got, tell me if this is what you got, 18, 118 thirds, and 14. Anybody get that? So, if somebody hands me a system of equations and they hand me a calculator, I'm RREFing every time, because that's the easiest thing to do. But if I have to use inverses, then I put in my coefficients, I put in my constants, and I multiply the inverse of the coefficients times the constants, and that will give me my answer. If, Sabrina, we RREF,
Yeah.
that would be exactly what we would get, because that's the answer.
Oh, so it
to the
doesn't matter?
system. No, we're just following the directions. All right, number 8, we gotta at least get this set up before we go to lunch. Number 8. We know that it takes 2 points to write the equation of a line. Right, you know that. It takes 2 points to write the equation of a line. Well, we are writing the equation of a parabola, a quadratic. So it takes 3 points to do that. Now, if you happen to have the vertex, you can get by with 2, but you really need 3, just at random, if the points are just random. So, these are the random points on this parabola. There is one parabola that goes through those 3 random points. Any thoughts on how we might figure out what the, like 2x squared plus 3x plus 5 or something? Anybody have any ideas how we might figure that out? What? Go with it. Now, who cares? What's the worst that can happen? You'll be wrong and we'll all laugh. I'm kidding. Plug the numbers in, absolutely. If you put in a 1, excuse me, a -1 for the x's, then it should all add up to 5, right? So 5 equals 1a minus b plus c. I just put 5 here, and -1 squared is 1, -1, just like that. Yeah, and what's gonna happen? I'm gonna get 3 equations, and it's gonna look just like this. Right? What's my second equation? This is -1. Now I'm putting in 2. So that's gonna be 4a plus 2b plus c. And then 13 equals 9a plus 3b plus c. All right, I want you to RREF that, and then we'll go to lunch, okay? Now, do be careful. I have my equations kind of backwards. So it's 1, -1, 1, 5. 421, negative 1,931,13.
3 by 4.
I really don't care how you solve it. I said RREF because that's my favorite, but you can do inverse, if that's what you want to do.
That theory is the summation, so that's that,
Yeah.
I got 4, -6, -5.
These numbers at the back.
So my job is to write my equation, so y equals 4x squared minus 6x minus 5.
Like, does it have to be like, even though we wrote it that way, like I can't do 5, 1, -1, 1, I have to do it the other way around.
I'm not sure. I mean, if you did that, then this column would for sure be the answers. That the problem is, it's not gonna come out in row echelon form. You see what I mean? Because that can't, that number right there cannot be a 5. It has to be a 1. You see what I'm
I
saying?
got,
Yeah. Okay, everybody okay with that? Okay, quick comment. What if this had been a 4th degree equation? I mean, a 3rd degree equation. AX cubed plus BX squared plus CX plus D. Could I do exactly the same thing? Yes, but I would need 4 points, right, to generate that. All right, go to lunch. I want you back at 50. Everybody back at 50.